Module 4, Advanced Topics and Practical Training Lesson 13 to 16. Advanced Topics in Air Conditioning and Refrigeration. Hello Fox, welcome to this advanced lesson on air conditioning and refrigeration, focusing on cutting-edge technologies such as inverter technology and variable speed systems, as well as heat pumps and heat recovery systems. These advancements offer significant benefits in terms of energy efficiency, performance, and environmental impact, making them critical topics for professionals in the HVAC industry. Inverter technology and variable speed systems. Inverter technology is a prominent advancement in air conditioning systems. Unlike conventional systems that operate at full capacity or not at all, inverter-driven units vary their output according to the temperature needs of the space. This continuous modulation allows for more precise temperature control and improved energy efficiency. The core of inverter technology lies in its variable frequency drive VFD, which adjusts the motor speed of the compressor. By varying the compressor speed, inverters allow air conditioners to maintain constant room temperature without fluctuations while consuming less energy. This results in substantial savings on electricity bills and reduces wear and tear on components, prolonging the system's lifespan. Benefits of inverter technology: energy efficiency. By adjusting the compressor's speed, inverter systems reduce power consumption during partial load conditions, enhancing overall efficiency. Rapid cooling and heating. These systems can reach desired temperatures quicker than non-inverter models. Stable temperature control. Inverter technology ensures minimal temperature fluctuation, offering greater comfort. Noise reduction. Since they operate at lower speeds when possible, these systems run more quietly. Variable speed systems. Variable speed technology extends beyond the inverter and applies to different components within the HVAC system, including fans and blowers. By modulating the speed of these components, the system matches the heating or cooling output to the load demand more accurately. This nuanced control leads to enhanced comfort, better humidity management, and improved energy usage. Advantages of variable speed efficient load matching. Systems adjust their output dynamically, reducing energy waste by matching the actual heating and cooling requirements. Improved air quality. Continuous fan operation assists in superior filtration and humidity control. Quiet operation. Running at lower speeds translates to quieter operation overall. Heat pumps and heat recovery systems. Heat pumps are versatile units that can provide both heating and cooling by transferring heat between the indoors and outdoors. They are especially efficient in moderate climates and boast an impressive coefficient of performance COP compared to traditional heating methods. By leveraging refrigerant cycles, they move heat rather than generate it, leading to significant energy savings. Types of heat pumps. Air source heat pumps. These systems extract heat from outdoor air and are most effective in milder climates. Ground source heat pumps. Geothermal. Utilizing the Earth's stable underground temperatures, these pumps provide high efficiency even in extreme conditions. Water source heat pumps, ideal for areas with available water bodies. They offer consistent performance. Heat recovery systems. Heat recovery systems enhance the efficiency of HVAC systems by reclaiming waste heat from conditioned spaces or exhaust air. This reclaimed energy can then be reused for other heating or preheating processes, resulting in reduced energy consumption and operational costs. Key benefits of heat recovery. Reduced energy costs. By recycling waste heat, these systems cut down on additional energy requirements. Environmental impact. Decreasing energy usage lowers carbon emissions, contributing to a greener planet. Improved system efficiency. Integrating heat recovery enhances the overall system's performance and resource use. Here's a summary of heat pumps and heat recovery systems. Heat pumps. 1. Definition: heat pumps are systems that transfer heat energy from one location to another using refrigeration. 2. Types: air source, ground source, and hybrid heat pumps. 3. Benefits: energy efficient, environmentally friendly, and cost effective. 4. Applications: space heating, cooling, and water heating. Heat recovery systems. 1. Definition: heat recovery systems capture and reuse heat energy that would otherwise be wasted. 2. Types: heat recovery ventilation, heat exchangers, and heat recovery chillers. 3. Benefits: energy savings, reduced greenhouse gas emissions, and improved indoor air quality. 4. Applications: commercial, industrial, and residential buildings. Key components. 1. Compressor. Compresses refrigerant to transfer heat energy. 2. Condenser. Rejects heat energy to the surrounding air or water. 3. Evaporator. Absorbs heat energy from the surrounding air or water. 4. Heat exchanger. Transfers heat energy between fluids. Advantages. 1. Energy efficiency. Heat pumps and heat recovery systems can reduce energy consumption by up to 50%. 2. Environmental benefits: reduced greenhouse gas emissions and minimized waste heat. 3. Cost savings: lower energy bills and extended equipment lifespan. Challenges and limitations. 1. Higher upfront cost, increased cost of heat pumps and heat recovery systems. 2. Complexity: requires specialized training and expertise for installation and maintenance. 3. Space requirements: heat pumps and heat recovery systems require adequate space for installation. Executive summary. Here's a summary of advanced topics in air conditioning and refrigeration. Inverter technology. 1. Inverter-driven compressors improve efficiency and reduce energy consumption. 2. Variable speed operation allows for precise temperature control and reduced energy consumption. Heat recovery systems. 1. Heat recovery ventilation, recover heat energy from exhaust air and transfer it to fresh air. 2. Heat recovery chillers, recover heat energy from chilled water systems and transfer it to hot water systems. Advanced refrigerants. 1. Natural refrigerants, carbon dioxide, hydrocarbons, and ammonia offer environmentally friendly alternatives to traditional refrigerants. 2. Low GWP refrigerants, refrigerants with low global warming potential such as HFOs and HFCs, reduce environmental impact. Smart air conditioning and refrigeration systems. 1. IoT-enabled systems monitor and control systems remotely using internet-connected devices. 2. Energy management systems optimize energy consumption and reduce waste using advanced algorithms and sensors. High-performance air conditioning and refrigeration systems. 1. High-efficiency compressors improve system efficiency and reduce energy consumption. 2. Advanced coil designs enhance heat transfer and reduce pressure drop. Sustainability and energy efficiency. 1. Energy-efficient design optimize system design for minimal energy consumption. 2. Sustainable refrigeration use environmentally friendly refrigerants and minimize waste. Emerging trends and technologies. 1. Magnetic refrigeration use magnetic fields to refrigerate, potentially replacing traditional vapor compression systems. 2. Thermoelectric cooling use thermoelectric materials to cool, potentially replacing traditional vapor compression systems. Here's a summary of inverter technology and variable speed systems. Inverter technology. 1. Definition: inverter technology uses power electronics to convert AC power to DC power and then back to AC power at a variable frequency. 2. Benefits: improved efficiency, reduced energy consumption, and increased system reliability. 3. Applications: air conditioning, refrigeration, and heat pump systems. Variable speed systems. 1. Definition: variable speed systems use inverter technology to adjust the compressor and fan motor speeds to match changing cooling demands. 2. Benefits: improved efficiency, reduced energy consumption, and increased system reliability. 3. Applications: air conditioning, refrigeration, and heat pump systems. Key components. 1. Inverter board converts AC power to DC power and then back to AC power at a variable frequency. 2. Compressor Operates at variable speeds to match changing cooling demands. 3. Fan motor. Operates at variable speeds to match changing cooling demands. Advantages: 1. Improved efficiency, reduced energy consumption, and increased system reliability. 2. Increased comfort, more precise temperature control, and reduced noise levels. 3. Extended equipment life, reduced wear and tear on system components. Challenges and limitations: 1. Higher upfront cost, increased cost of inverter technology and variable speed systems. 2. Complexity, requires specialized training and expertise for installation and maintenance. 3. Compatibility issues, may not be compatible with all system components and configurations. In conclusion, understanding and leveraging these advanced air conditioning and refrigeration technologies is essential for any HVAC professional aiming to optimize performance, improve efficiency, and reduce environmental impacts. As these technologies continue to evolve, staying informed about the latest developments will provide a competitive edge in both residential and commercial applications. Keep exploring and implementing these systems to meet the ever-growing demand for sustainable and efficient climate solutions. We hope to have you again in the next lesson. Happy learning, folks!